Welcome to the Explainer. So, have you ever stopped to think about what a mountaineer on Everest, a fighter pilot pulling a tight turn, and a deep-sea diver have in common? I mean, they seem like totally different worlds, right? Well, today, we're going to dig into the physiology of human survival. What happens when our bodies are pushed to the absolute breaking point? Okay, so here's the plan. First up, we're going to uncover the one critical thing that connects all these insane challenges. Then, we'll see how it all plays out when you go way up high, when you're going incredibly fast, and when you dive deep underwater. And finally, we'll get to the really cool part, the ingenious ways we figured out how to hack our own biology to survive.
Yeah, I mean, at first glance, these things couldn't be more different, right? You've got a mountaineer fighting for every breath in thin air, a pilot getting slammed by crushing G-forces, and a diver exploring a world of, immense, heavy pressure. So what's the link? What's the one thing that ties them all together? Well, it turns out their survival is governed by the exact same fundamental principle.
And it all comes down to this one thing, partial pressure of oxygen. You can call it PO2 for short. Seriously, this is the main character in our story today. See, the air we breathe is always about 21% oxygen. That doesn't change. But what really matters to your body, what it can actually use, is the pressure of that oxygen. Think of it like this. Higher pressure literally crams more oxygen molecules into every single breath, making it way easier for your lungs to grab onto them. And that single variable, that's the key to surviving all of these extreme environments.
All right, so let's see this in action. We're going to start our journey by heading up, way, way up. We're talking about the world of mountaineers and pilots, where the air gets dangerously thin and the number one enemy is that critical lack of pressure.
Just look at this. See how dramatically that available oxygen, that PO2, just falls off a cliff as you go higher. At sea level, no problem. The pressure's great. But get this, climb to 50,000 feet and that pressure drops by almost 90%. And remember, the percentage of oxygen in the air is still the same. It's just that the molecules are so spread out, you're basically suffocating with every single breath.
And your body's reaction to this oxygen starvation, which is called hypoxia, is, well, it's fast and it's bad. At just 12,000 feet, you might start feeling a little drowsy, maybe even kind of euphoric, but your judgment is already going out the window. Push it to 18,000 feet and your muscles start twitching, totally out of your control. And then, at 23,000 feet, if you haven't had time to acclimatize or you don't have supplemental oxygen, an unacclimatized person falls into a coma. And eventually, they die. It's that serious.
Okay, so we've talked about the slow, creeping chemical stress of having no oxygen. Now let's do a complete 180 and talk about a totally different challenge, the brutal, instantaneous physical stress of acceleration. Yeah, we're entering the world of fighter pilots, where the simple act of making a turn is basically declaring war on your own body. So what are these G-forces actually doing to you? Well, it's all a battle for your blood. During a really high-speed turn, those positive Gs are literally pulling all the blood from your head down to your feet. Your heart just can't pump hard enough to fight it, so your brain gets starved of oxygen. First, your vision starts to tunnel, and then complete blackout. Now flip it. Negative Gs do the exact opposite. They force blood violently up into your head, causing this painful blood-filled readout. And just to put that number in perspective, we're talking about an insane amount of force. Sustaining a positive G-force of over 20 times the force of gravity, that's not just about blacking out anymore. It can physically fracture a pilot's vertebrae. I mean, our skeletons just were not built to handle that kind of load, period. Okay, so now, let's plunge deep into the ocean. And here, the problem completely flips on its head. It's not about too little pressure anymore. It's about having way, way too much. For every 33 feet a diver goes down, another entire atmosphere of pressure gets piled on top of their body.
And divers have this really kind of haunting name for what happens down there. They call it the raptures of the depths. And what they're talking about is this strange, super dangerous thing called nitrogen narcosis. See, under all that intense pressure, the nitrogen in the air they're breathing, which is normally harmless, starts to act like an anesthetic. It literally dissolves into the body's tissues and starts messing with your brain. And the deeper you go breathing normal air, the worse it gets. At about 150 feet down, a diver might start to feel kind of drowsy, a little too carefree. But push it past 250 feet, and they can become so clumsy and confused, they're basically useless. And you can imagine making a catastrophic mistake down there. Well, that's an environment with absolutely zero room for error.
But the danger isn't just about going down. Oh no, coming back up can be even more deadly. See, when you're down deep, all that nitrogen from the high pressure dissolves into your body fluids. If you come up too fast, the pressure drops, and that dissolved nitrogen starts to fizz out of your blood. I mean, exactly like opening a can of soda. These bubbles can get stuck in your blood vessels, causing this agonizing pain they call the bends, or much, much worse, paralysis and even death.
So, okay, faced with all these lethal challenges, how in the world have we managed to survive any of this? I mean, we can't just change our basic physiology, right? So, we have to get clever. This is where science and engineering come in to create these brilliant solutions, letting us effectively hack our own biological limits. Just think about the power of one simple hack. Remember that 23,000-foot ceiling for survival we talked about on just normal air? Well, what if you switch to a mask that feeds you 100% pure oxygen? Get this, you more than double that ceiling. It just floods your lungs with that higher partial pressure of oxygen, pushing the absolute limit for consciousness all the way up to a staggering 47,000 feet. It's a total game changer.
And what's really incredible is how we can take a danger and turn it into a powerful medical tool. We can actually recreate that hazardous, high-pressure environment of the deep sea, but safely inside a hyperbaric chamber. You have a patient breathe pure oxygen at that high pressure, and you can super saturate their blood with it. And this doesn't just reverse the bends. It also kills certain types of bacteria. It counteracts carbon monoxide poisoning. We've literally turned something that can kill you into a life-saving therapy. So, what does this all prove? It proves that our bodies are incredible, but they're also exquisitely fine-tuned for a very, very narrow slice of conditions right here on Earth's surface. But here's the cool part. While our biology definitely has its limits, our ingenuity maybe doesn't. Our understanding of science lets us engineer our way past our natural boundaries, which, leaves us with a pretty big question. As we keep pushing further into the sky, deeper into the sea, are we finally reaching our biological limits, or is this just the beginning of what we can achieve?